Yeah, Advait. Okay. So, guys, today we are going to talk about HaloArenes. Okay. So, HaloArenes means it will be AR, aromatic, and any halogen. You can also show it like this. Draw the aromatic benzene ring and put a halogen over here. Okay. We can also write it like this. You write phenyl group and put a halogen. So these are the three ways how we write halogens. This halogen can be chlorine, fluorine, bromine, and iodine. All right. And what does AR represents? Aromatic, benzene ring. Clear? So if chlorine is attached, we call it as chlorobenzene. If bromine is attached to the ring directly, we call it as bromo. If iodine, iodobenzene, and if fluorine is there, we call it as fluorobenzene. All right. Now, apart from this, you really need to understand the resonance, okay? The resonance of halogenes, okay? Though in the last class towards the end we have discussed, but again I'm going to brief you about it, okay? And now please see here. So first of all, please remember some patterns I'm going to give you, okay? If you see that sequence, if that you see that in pattern, then only we can say resonance will happen, right? Shubham, you got it now? Yes. So what are those patterns? One is pi, sigma, plus. Now tell me, what does plus indicates? The plus charge in chemistry. I mean here in organic chemistry, deficiency, right? The loss. Plus means, can we say plus means vacant p orbital? Vacant p orbital. Now again you will ask me one more question. Sir, why did you specify it on p orbital? Why you haven't mentioned about s orbital, d orbital, f orbital, right? There are SPDF, four type of orbitals, right? But why did you specify p orbital only? Because organic chemistry, you're talking about carbon. And if I show you the carbon electronic configuration, it's 1s2, 2s2, and 2p, how much? 2. So last shell electrons are in p subshell, right? So if anything is will be vacant, it will be p. That's why I wrote p subshell. Avantika, you're clear, no? This is one sequence. Another is pi, sigma, and a negative charge, or we can say lone pair. Negative charge means extra electron. Extra means lone pair. Lone pair means which are not participating in the bond formation, right? They are extra. Clear? So if you come across this sequence, there are two more, but right now, as of now, you need to focus only on these two. So if you come across this sequence, okay, you can take one more, that is pi, sigma, pi, pi, sigma, and pi. So if you see, the first two sequences are common in all of them. Pi bond, sigma bond, then plus, minus, or pi. Pi means the multiple bond, double or triple bond. Sigma means single bond, right? So if you come across any of these three patterns, which we call it as, what these patterns are called as? Conjugation. Okay. If you come across with any of these, hi Tanuj, yeah. So if you come across with any of these sequences or conjugation, then only we say resonance will take place. Then resonance can happen, or resonance is possible. Okay. If you see any of these, then resonance is possible. Okay. I hope it's clear to everyone. Guys, got it? No? Okay. Vaibhavi, you got it till here? Okay, all right. Now, now let me give you one example. Okay, we will take the example of this. Tell me what is the structure here? It's chlorobenzene, right? You all can see this is a, yes, chlorobenzene. Hi, Ananya. Now, in this chlorobenzene structure, you will see what we need to look, find any of these pattern, pi sigma plus, pi sigma minus, or pi sigma pi. First of all, this entire ring has pi sigma pi. On top of that, if you see, there is pi sigma lone pair, right? I mean, three lone pairs are there, but only one will participate. Okay, so you can see that pattern we have got. Pi sigma pi is within the ring. Outside with outside, what you have pi sigma lone pair. So, and it has to be continuous. It's not like pi sigma, then nothing, and then lone pair. It's not like that, okay? It has to go in a row. Okay, so pi sigma lone pair when you have, so how things will happen now? First of all, this lone pair will come down here. Lone pair will come to sigma down. One step down, not two step. Now this carbon, if it has one extra electron, carbon can have only maximum of four bonds. Then this pi electron will be pushed to the next one. Clear, no? Got it? So now tell me what will be the next structure. Guys, this is important. That is why I am explaining the again, okay? Yes. Right. So all of you see this carefully. So what will happen? First of all, because now three lone pair, one pair is donated, only two is left. And because chlorine is donating, so can we say there will be a plus? And now lone pair came here, so can we say double bond came here? Okay. And here the pi electron shifted here, so can we say it will be like this? Minus extra electron, right? If you have a loss, it's plus. If you take extra, it's minus. Simple. Minus means the lone pair, okay? Same thing. Okay. So, and here nothing has happened, so put it as it is. Now, do you see the same pattern again? Pi sigma lone pair. Again, same story. Now, this lone pair will go here and this pi will shift here. Got it? No? So, those who know, please complete it. And those who are learning, please see here. Online, do the same thing. If you are already knowing it, please finish it off. Now, so copy the structure first where nothing has happened as it is. Where change has made, there we will write. So now how do you write it here? So kindly see this. This double bond is here as it is. Cl2 lone pair with its plus charge. Now what happened? This lone pair came here, so double bond will be here, right? And this pi electron shifted here, so negative charge will come here. This is our third structure. Remember, resonance whenever happens, it happens in one direction. It doesn't go reverse. If you go reverse, you will end up with the same structure. So make sure you, if you are going clockwise, you go clockwise. If you are going anti-clockwise, you go complete one cycle of anti-clockwise until you are finding the pattern. Okay? Online, is everyone clear? Please tell me. Tanuj, did you get this? Shreyan, you got it, no? Okay. So now, after this, what is the next thing? Again, you will see a pattern. Pi sigma lone pair. Pi sigma lone pair has came up again. Yeah, hi Pranav. Now, please see this. So this will shift here. This will shift here. Got it now? Guys, after this, I'm going to give you one additional work. Okay. So please focus. Now, we will draw the next structure. So our next structure will be, now this has shifted here, so double bond came here. This pi shifted here, so negative charge came here. I think it's clear for everyone. Got it? The fourth one. Okay, Tanishka. One, two, three, four. So all these resonating structures you are drawing, they are also called as canonical forms. Okay, in the NCRT book. Now tell me the last and final step. You can see the pattern here. It's pi, sigma, lone pair, right? Pi, sigma, lone pair. So what will happen? This pi will shift here and this lone pair comes here. Finally, from where we started, we got back. And our resonance is complete. So Cl has got back its all the lone pair and double bond here, here, and here. Perfect. You can see that. This means our resonance is over. This is your fifth canonical form. Okay. Now finally, yes, Ritvik. Now we will draw the hybrid. Sum total of all these structures. Now let me tell you one thing. It will break your heart a bit, but yes. So organic chemistry mostly it's hypothetical. Okay. Applications are real, but it's mostly the concepts are hypothetical. Similarly, all these structures are also hypothetical. They don't exist in real. But when we combine them up, okay, then the structure we get is hybrid. Combination of all five. That's real. And whenever we comment on the any organic compound properties, we comment on hybrid, looking at the hybrid. We never comment it on looking at resonating structures. But we need resonating structure to get the hybrid. Clear? So now, first of all, let's draw this hybrid. So how do we draw the hybrid? First of all, draw the skeletal structure. Now, if you see this chlorine had a positive charge. So can I say it will be partial positive? We represent the positive charge in hybrid as partial. So delta we will use. The symbol we use is delta. So partial positive. Now at these positions, you can see we will put partial negative, right? You can see. Okay, because negative charge was here, it was here, and it was there, right? So wherever negative charge was, we put it as negative partial. After that, wherever the double bond was, we will draw the dotted line. It means you can say double bond is present at each and every carbon. So entire circle will put. And plus the double bond was here also. So this is our hybrid. We are going to give a comment on this structure. Okay. All right. Online, is everyone clear? Guys, please confirm. Everyone? Okay. Now, if you look at this structure carefully, you will see there is a partial double bond character, right? Between chlorine, and carbon, right? So you can write due to, it's an important point what I am mentioning here, due to partial double bond character, right? Between carbon and halogen atom. You can see that carbon and halogen, right? There's a carbon and there is a halogen. So due to this partial double bond character between carbon and halogen, okay, they do not give, okay, nucleophilic substitution reaction easily. They do not give nucleophilic substitution reaction easily because nucleophilic substitution reaction happens only when one is removed, then the other replaces, right? If the one is not going to be removed, the other can't replace it, right? So this is the nucleophile here, right? The halogen, the chlorine is a nucleophile here, right? So if this is not leaving, the new one cannot come, right? Substitution will not happen. Clear for everyone? So that is why this point is very important and you have to show the resonance. Okay, that due to resonance, CX bond strength is very, very strong, right? Partial double bond character, and that is why it doesn't tend to give nucleophilic substitution reaction easily. Mark it as a very important board exam question because it has came almost in every year. Somehow directly, indirectly in MCQs or direct, in 2 markers, in 3 markers they ask. All right. But this is the first reason. There is one more reason which I have discussed in the previous class. What was that? If you look at this carbon, right? If I draw you the halorene, if you look at the structure, the carbon over here, the carbon over here is, what is the hybridization of this carbon? Yes, it's sp2. Why it is sp2? Because there are 3 sigma bonds, right? 3 sigma bond means 1s and 2p, sp2. Okay. So sp2 structure, it means it has 33.33% of S character, right? It has 33. How it is 33.33? Because it has 1s and 2p. So 1 plus 2 is 3. And how many s is there out of 3 total? 1. So 1 by 3 is 33.33. Clear for everyone? So remember here one important thing. The greater the S character, yes, very good. So greater will be the electronegativity. And when electronegativity is more here in this case, so basically this carbon halogen bond will be strong because they will hold it tight. This carbon also has more electronegativity. This halogen also has more electronegativity, right? So their bond will be very, very strong, right? They both will be attracted to each other, right? So that means CX bond, it's difficult to break the, it is difficult to break CX bond. It's difficult to break the CX bond. Another reason why it doesn't tend to, another reason, okay, halorine is less reactive towards SN reaction. So guys, take a note. That is why this sp2 and S character is the another reason why halorine they don't tend to give the nucleophilic substitution reaction. It's very, very important. Okay. I hope online is everyone clear. Arnav, Shaurya, Tanishka, Tanvi, Vaibhavi. Okay. All right. Guys, take a note of this. Once you're done, let me know. Argon. ARX is halorine. It's halomeritic, no? It's a way how you write, you got the ARX means it's a halorine, right? AR is a aromatic ring. Okay. Okay. Everyone done? Guys, now let's learn another interesting thing. That what if we still want to carry out the nucleophilic substitution? See, we learned they are not reactive towards SN reaction, right? But what if we want to still carry it out? So we have to do it forcefully, okay? So write it down. Online, did everyone write this part? Should we continue? Kindly confirm. Okay. So now write it down. A method called as DOS process. Write it down. DOS process. Write down. HaloArene can give nucleophilic substitution reaction under drastic conditions. So under drastic conditions, we will carry out forcefully, okay? So understand what are the drastic conditions, guys. So first of all, you take the example. Guys, got it, no? And first thing you will do here is you will add the NaOH. Guys, got it, no? You will be adding here is NaOH under very high temperature and high pressure. Advitya, can you tell me what is the temperature and pressure conditions for carrying it out? Yes, 623 Kelvin and pressure is how much? Very good, 300 atm. You know, where do you find this pressure? You know, where the submarines dive into, right? That is the pressure, 300 atm, deep in the ocean. All right. And 623 Kelvin means how many degrees Celsius, guys? See, it will be 350 degrees Celsius, right? It will be 350 degrees Celsius because 273 is 0 degree. So after 273 till 623, it will be 350. All right. 273 to 673 is 400. 73 and 23 difference is 50. So 350. Okay. Clear for everyone? So you can see this is the drastic condition we were talking about. High temperature and high pressure. Okay. Now what will happen? You are not using one NaOH. You are actually using 2 moles of NaOH. How many moles of NaOH are you using? 2 moles of NaOH. Okay. Now understand what's gonna happen here. Okay. First of all, in this reaction, everyone pay attention very carefully. Na and Cl will be removed. Okay. So minus NaCl. Guys, got it? No? Yeah, I will explain. Second thing what will be removed is the H2O water will be removed. Got it? So what is left now? Online, everyone tell me what is left? Ananya, what is left? ONA, right? So understand here O minus Na plus. That is what you'll get. Intermediate, right? We call it as, what's the name here? Sodium, what? Yes, very good. Sodium phenoxide, okay, very good. phenoxide. Okay. Now, after this, after adding a base, you will add acid. So we will add H2O. So guys, we are adding H2O, H plus OH minus. So NaOH will be taken out. After that, what will happen, guys? NaOH, clear? So NaOH, which was used in the reaction, is now recovered. So H plus will go to O minus. So what do we get here? Yes, we will get phenol. So this is how we carried out forceful nucleophilic substitution, okay? The DOS process. Clear for everyone? This is the method. This reaction is called DOS process. It's very, very important, the name. Okay. Please take a note of it. Now, after this, I'm going to explain you what are the reactions the halogen gives, because of this ring. Okay. Yes, Tanishka. No, only for this reaction, only for this one. Okay. Got it, no? So, guys, online, did everyone write it? Should I carry on? Continue to the next part? Pranav, confirm this. Did you wrote? Okay. So, guys, next part is write down electrophilic substitution reaction. Electrophilic substitution reaction. Okay. Nucleophilic substitution reaction we have learned. Now we are learning electrophilic substitution. It means one electrophile replaces the another. All right. So, guys, please see here. We already have seen. Tell me where you have seen this. Sometime back we have seen when we draw the resonating structure of halorine, we saw this hybrid structure, right? Correct? Now, I have to tell you something here important. When a ring is there, okay? When a ring is there, guys, and if any random group is attached here, okay? Say Y, okay? Sure, see this very carefully. Now, what I'm trying to tell, if you have any random group attached here, okay, to the ring, right, directly attached, then this group is called side chain. What do we call it as? Side chain. And with respect to the position of side chain, this there is where side chain is attached, right? So the next to the side chain, the immediate next positions are called ortho positions. What do we call these positions? Yes, ortho. So how do you decide ortho? The positions immediately next to the side chain group, okay? Next to ortho, these positions are called meta, okay? And next to meta, the only position is para. It means there will be two ortho, two meta, and one para. Okay, best way to remember it by a trick Om Prakash, OMP. Remember the name Om Prakash. So OMP. That's it. Okay, is it clear? No. So now, where is the side chain here? Now the side chain is here, right? So ortho meta para positions have changed. Now immediate to this carbon, these two are ortho. Correct? This is ortho, this is ortho. So who decides the position of ortho, meta and para? Side chain, yes. So this is ortho, this is now meta, right? This is meta and what is this? Para, last one. So what do you see in this structure? We see the electron is negative means electron rich area, right? Positive means deficiency, negative means excess. You have learned that, right? Online, is everyone getting it? What I'm trying to tell. So, electron rich area is present in ortho and para. Can we say that? Now, so understand here, electron rich area is at ortho and para positions. In case of haloarenes, right? So because electron rich area is present at ortho and para positions, because of that we call them ortho and para directing groups. We call them ortho and para directors. Okay? Ortho and para director, what does it mean? What does it mean by ortho and para directors? It means they direct incoming, they direct incoming electrophile. See, this is how we represent electrophile, E plus. Okay. So they direct electrophile, incoming electrophile at ortho and para positions. I hope it is clear. Got it, everyone? They direct incoming electrophile at ortho and para positions. Why? Because electron rich areas are at ortho and para. Why? Because electrophile are electron lovers. They are, phile means love, affinity. Okay, phile means love, phobia means, like you have studied hydrophilic and hydrophobic. Hydrophobic means doesn't like water. Hydrophilic, phile means love, affinity. Okay, is it clear? So electrophile are electron loving species. Why they are electron loving species? Because they are electron deficient species. They don't have electron. So they will attack only on those areas where they get more electrons. And what are the areas indicating more electrons? The negative charges. So it's all connected. You are getting it right? Huh? Ortho and para. So you got it, no? We are discussing haloarenes, right? I'm talking about that. Is it clear? Remember, electrophile, if you don't know, write it down. Electrophile are electron deficient species, right? And they attack at they attack at electron rich areas, and that is ortho and para positions. We have seen this in resonance. Online, is everyone clear about this concept? Ananya, Shreyan? Okay. Now, there's something more you need to learn. Okay. Guys, understand here one thing. Okay. Okay. First, write it down. Let me know once it is done. Then I'll talk about the next part. Ritvik, everything's clear. Yes. Yes. The haloarenes, right? Yes. Haloarenes are always going to be ortho and para directing. Always. Okay. Clear, no? In case exception, I'll tell you. As of now, there is no exception. Okay. Now. So guys, now understand here one thing. You have seen the resonating structure of haloarenes, right? We have seen that how it was resonance was happening in the first step, the pi sigma lone pair, right? Correct? We saw the conjugation and how it happened. The lone pair came here and it went there, right? Correct? The first step. So now tell me, the lone pair is going inside the ring or outside? Where the lone pair is directed? Inside or outside? It's coming inside, right? It's not going away, it's going towards, right? So it means you can see when lone pair is directed inside, we call it as it shows plus R effect. Which effect? Plus R or plus M. Resonance or mesomeric, right? Got it now? So when lone pair is directed towards the ring, it shows plus R or plus M. Okay? Got it now? And when you have plus R or plus M, we call them ring activating group. What do we call them? Ring activators. So who is the ring activator? When the halogen is attached with the ring, it donates the electron in the ring due to plus R and plus M. It's ring activator. I hope it's clear. Ring activator, because lone pair is donated. You will come across these terminologies. Ortho and paradirecting, ring activating, they all are same. Got it, no? Because ring is coming inside. Because electron is directed inside. Okay, online everyone got it, no? Okay, clear? Next. Now there is a mystery here. The mystery is, guys, carefully see this. Here, one thing you people have seen, that there is a plus M effect, right? You have seen that plus M is happening. But at the same time, halogen is highly electronegative, right? Halogen is highly electronegative. So when it's highly electronegative, it is an electron withdrawing group. Ananya, you're getting it? Avantika, it's an electron withdrawing group, right? Electron withdrawing group means it's minus I effect. Plus M always dominates minus M, but in case of haloarenes, it's minus I dominates plus M. Got it? No? Only in this case, write a note. Only in this case. Guys, right? Let me confuse you more, okay? That's the best part of the organic chemistry. Okay. Right now you have learned it's orthopara, it's ring activating, always ring activating. I think Sid also asked one question, sir, is it always? I said yes, it is always. Now I have started confusion, okay? Now I told that halogen is there, it's an electron withdrawing group, it will pull the electrons, right? So in this case, if you see, electrons are going away from the ring. See, due to plus M, it's coming in the ring. So it's like there are two factors are coming, two concepts. One says electron goes inside the ring, another says it goes away from the ring. Then how it can be ortho and paradirecting? It will become ring activating, right? Because minus I effect means ring deactivator. Ring deactivator, right? It is a ring deactivator. Correct, no? Clear? And also I told plus M dominates over I effect, okay? But in case of haloarenes, it's minus I dominates in this case. Is it clear? Now the confusion starts. Then how it can be a ortho and paradirecting? Okay, so take a note. It is observed, it is observed, okay? Shaurya, you have understood till here what I have told? Okay, but now write it down. It is observed despite minus I dominates over plus M. It is observed that despite minus I dominates over plus M in case of haloarenes, Ritvik, you getting it no till here? In case of haloarene, still still we see, wait, haloarenes are ortho and para directing groups. Ortho and para directing groups. Now this confuses everyone the most. How? That question comes in everyone's mind. That, sir, first you told it's ortho para directing, ring activating because of plus M. We understood. Then you told because halogen is there, it's a minus I effect. And then it because of minus I, it's ring deactivating. You know, ring deactivators, they send the electrophile at meta position. But still you are telling, despite minus I dominates over plus M, it is still according to plus M, not according to minus I. It is still ortho and para. How? That's the question. So guys, that part I will be discussing in detail in the entrance class. Okay, that is we doing on Saturday, right? So Saturday I'm going to give and go on details on this, and we do some relevant questions. Okay, but for now, please take a note of this. Okay, and yeah, one more thing I'll tell you that it's experimentally it is also observed the same thing. Okay, so basically in organic chemistry, what happens, or in inorganic chemistry, we first develop a theory, then we run experiments, and then we see that experiments and theory are mismatching. Then we develop theory according to the result of experiments. You got it, no? So there could be a lot of theories, and there are some, no theories also. They just say it happens like that. But I'm going to give you the most accepted theory, okay, as per the latest convention, and which they follow in JEE exams also. All right. So that we will discuss on Saturday's class, okay? But as of now, please take a note of it that it always remains ortho and para directing full stop. Is it clear? Online, is everyone clear? Please confirm. Huh? No, it's not an assumption, it's experimentally observed, okay? And plus it is proven also. Some theory is given that I'll tell you. What is, they ask in the entrance. All right. So what you have understood, the overall conclusion is it's ortho and para directing. Now let's learn those reactions, okay? So guys, now let's see the reactions. So now write down the reactions. So the first reaction we will see, that is, nitration. So guys, write down nitration reaction, okay? So in the nitration reaction, you can see you need to know the reagents. What is the reagent you will use? So the reagent you will use is HNO3 plus H2SO4 conc. So guys, you will be using these two acids, sulfuric acid and nitric acid, okay, for nitration. Now, from this reagents, you know what electrophile you will develop? You will get NO2 plus. This is your electrophile. Got it? So this electrophile will go at which positions? Ortho and para. So we will get the answer something like this. So one NO2 will be here, another NO2 will be at para. Guys, one more thing. Please see here. One will be ortho substituent, one will be a para. Okay. And what will be the major product and minor? These two things are formed. One will be in large quantity, one will be in more small. So remember, para will be always a major quantity, and ortho will be minor. Okay, less amount. Yes, Ritvik. No, nothing like that. Yeah, two products are there. What you're telling is retention inversion part, right? Yeah, similar to that, but it's not the same. Okay, got it? No, clear for everyone? Yeah, it's para is always the major. Okay, now if we write so this is the ortho substituent, ortho isomer. This is the para. Guys, can you tell me the okay name? We can't tell because I have not mentioned the halogen, right? Anyways, can you tell me the second one? What reaction is there? It is sulfonation. Sulfonation. Okay. So you can see here because we have seen electron rich areas are ortho and para. So that is why it has got two positions. Now, let me ask you one question. I mentioned electrophilic substitution. It means when one electrophile is added, another is removed. Now, the question to you all is who is removed? Who is removed? Yes, very good. From here, one hydrogen is removed, right? So the electrophile removed was H plus. I hope it is clear. Who is this electrophile removed? It was the H plus, right? So guys, sulfonation now you all have to see. No, all cases. It's not like that in both cases, right? If I don't remove this H minus is removed. Understand that. If I don't remove that, it won't be added, right? Because carbon cannot have five valencies, right? So guys, understand here. Sulfonation, what's the reagent? Aditya, can you tell me? Very good, but what H2SO4? Concentrated. So guys, Avantika, can you tell me what reagent do we will it come out from the conc H2SO4? See, what they give is SO3H. Got it, no? Or SO3H. Avantika, you got it, no? Okay. Now after this, so one will be at ortho, same thing. Once you know what electrophile is there, you know the answer, right? So halogen here, one will be here, SO3H, and another will be, so it's called sulfonic acid. When a benzene ring has SO3H, it's called sulfonic acid. Clear? Benzene sulfonic acid. Got it? No? Benzene sulfonic acid. Okay. Shreya, did you get it till here? All right, perfect. Tanvi, you got it? No? Okay. Third reaction now. Okay. Now we will discuss third reaction. Guys, it's a name reaction, so it's by default important. Friedel-Crafts alkylation, okay? FC alkylation. Alkylation means we add alkyl halide, okay? Alkylation means we will add alkyl halide. I hope it's clear to everyone, okay? All right. So you all can see this. Now, you add CH3Cl. And remember, we are adding alkyl halide. Alkylation means we add alkyl halide, okay? Got it now? And in the presence of anhydrous AlCl3. Now, what is AlCl3? It's a Lewis acid. What do you mean by Lewis acid? It means its octet is not complete. It's an electron deficient species, okay? If you look at the structure of AlCl3, see the central atom has octet is not complete. It's electron deficient, right? Got it, no? Lewis acid means electron deficient. Now, how the reaction will take place, guys? So understand this CH3Cl bond will break. This Cl will be taken up by AlCl3, right? So it will form AlCl4. So this will give rise to the formation of electrophile. So your electrophile will generate, and that is CH3 plus. Now you know where it will go. One will go at ortho and one will go at para. Perfect. So this will be your answer. It is so simple. So remember, when benzene ring contains CH3, it's called toluene. What do we call it? A ring with CH3 is toluene. So this is our answer. Okay. Next up we have, after this we will discuss Friedel-Crafts acylation. Uh, Tanuj, Advait, are you guys clear? Okay. So acylation means we will add acid halide group, okay? RCOCl, okay? Got it, no? So guys, let's discuss this acylation, how it will take place. Guys, see this? This is the HaloArene. In acylation, what I told, we add acid halide. So CH3COCl. Do you see that? Earlier it was alkyl halide, CH3Cl. This is acid halide, CH3COCl. Got it, no? And this will be added in the presence of anhydrous AlCl3. I hope it is clear. Anhydrous AlCl3. Same story. This bond will break. Cl will go to AlCl3, form AlCl4, and that gives the birth of the electrophile. This is how you'll get the electrophile. This is our electrophile. Got it, no? Now this will go and attach at ortho and para positions. So remember, whenever this group is attached, COCS3, it's called acetophenone. What do we call it? When COCS3 group is attached, it's called acetophenone. So we got ortho and para, where always the para is the major, okay? Weber, we got it, no? Okay, perfect. Because the positive sides attaches at electron density, Tanishka, right? So positive charge is at carbon, right? CO carbon. That is why it is attaching like that. Positive requires electrophile has the positive side, which requires more electron, right? That is why attachment happens like that. Okay. Yeah, if I write the name of the structure because I have, oh, here I have done a mistake, guys. You know what mistake was there? I have written CS3. It's Cl, no? This is Cl, this is Cl, right? Yes. Variation means I can change on the methyl ki jagah I put ethyl. Yeah. So guys, what will be the name of this reaction? So understand this is a ketone group, right? It's a functional group. This carbon will be number one. Tanvi, you're getting it now? This is number one. It should get the lowest number, right? And this will be number two, right? Here it is number one, two, three, four. So what's the name? 2-chloro. And what do we call this? Acetophenone. And what will be here? 4-chloro. This whole ring with COCH3 is called acetophenone. Tanvi, you got it, no? You can also call it as You can also call it as, with respect to this is the ortho position, right? Orthochloroacetophenone and parachloroacetophenone. You can also say it like that, okay? Got it, no? And similarly here, when a benzene ring with SO3H is there, it's called sulfonic acid. So what will be the name? Sulfonic acid, it's the highest priority, right? It's the functional group, right? So what will be the name in that case? So this will be ortho-halo, I mean chlorine, imagine if it's chlorine, right? So orthochloro sulfonic acid, parachloro sulfonic acid. Simple, got it, no? And what will be this? It's a nitro, right? So same way nitrobenzene, nitrobenzene. Clear for everyone? Okay. So guys, electrophilic substitution reactions we have learned, okay? And in haloarenes, what we need to see is the general chemical reactions. Okay, got it. There are more chemical reactions. So write down reaction with metals. So all of you write down reaction with metals. Reaction with metals. So one reaction is there is with magnesium, and I know you what they will form. So when you react this a haloarene. Wait, let me show it to you. So when you react the haloarene with Mg, guys getting it now? So what it will form? It will form RMgX. It's Grignard's reagent, right? It's a very useful reagent. I will show you the application later on. So it forms Grignard's reagent, guys. Please understand. And remember, it has 50%. So this carbon and magnesium bond, this magnesium and halogen bond, this is like ionic, right? It's 50-50. It's 50% ionic. And this carbon and metal bond, yeah, this bond, it's covalent. 50% is Covalent. So whenever you need to break the bond, remember you will break covalent bond, not the ionic bond. Okay. Online, is everyone clear? Please confirm. Okay. So guys, if you have the NCRT book, I want you to open it. Please take out the NCRT book. Let's see the reactions we have covered already. Let's observe. Yeah, part two. Yeah, haloalkene haloarenes. No, just go to that haloarene part. Okay, their method, they've explained haloarene. You can go to the chemical reactions. Go to 10.7 chemical reactions. Okay, so nucleophilic substitution reaction we have seen. Elimination reaction also we have to see. Yes, elimination is not there in haloarene. Guys, my bad. It's 10.7.2 reactions of haloarenes. Do you see that? Where they have mentioned about Victor Grignard, the scientist picture is given, right? Picture of Victor Grignard. Yeah, see, I have an old book, old version. So that is why I think you possibly have the new one, right? Can you all see that? Yeah, Ritvik, can you loudly tell the page number so everyone can find? 181. Okay. Online, can everyone refer to the page? Ananya, Vaibhavi, Tanuj, Shreyan, everyone. See, we have discussed the DOS process, right? All of you check. We discussed halogenation, nitration, sulfonation, right? Okay, halogenation I haven't told you. That also I need to add, my bad. Yeah, it's about to come. Yeah, that's what I'm checking on. Yeah, reaction with metals we are discussing, right? Okay, so let's complete that. After that, I'll tell you halogenation also, okay? Halogenations I probably have missed. So now, all of you, let's see the next reaction, guys. So the next reaction is with sodium. Can you all see? So how reaction will happen? See this. You will take this halorine with 2 sodium because we will be using 2 halorenes. Okay, guys, please see this reaction. It is not a Woods reaction. Okay, Woods reaction happens in case of haloalkanes. This is haloarenes. So guys, see this here. What's happening? Uh, a sodium will take out these halogens. So you will remove 2NaX, right? As a result, this ring will join to form biphenyl. What do we form? RX. Yeah, that was Woods. This is not Woods reaction, okay? In this reaction is called as Fittig reaction. What do we call? This is called Fittig reaction. Everyone take a note of this. Okay. Online, is everyone clear? Please confirm. Okay, it's very similar to Woods. It's nothing wrong to say that it's similar to Woods reaction, right? And one more reaction is there. When you take one alkyl halide and one aryl halide, okay? Guys, see this? One alkyl halide, one aryl halide, right? In that case, what will happen? You will get toluene. Guys, see this? Same story. 2NaX is removed. Now this reaction is half Woods, half fatigue. It's called Woods fatigue reaction. This reaction is Woods fatigue reaction, and this gives you toluene. This is called toluene. This is called diphenyl or biphenyl. Yeah, no, it is not mentioned, but it is also there. Okay, you need to know. It's the same. They all the reactions are same, right? There's no difference. You can see that fatigue Woods and Woods fatigue. Okay, okay. Students, please confirm. Did everyone got it online? Okay. Okay, yeah, I have missed one. This halogenations also. Okay, I'm going to tell you halogenation, though it's the same. It's not a problem. So, guys, I've missed the halogenation. Write down the headline halogenation. Halogenation means you'll add a halogen on a halorine, right? So, this is the halorine. Now you'll add Cl2, assuming it's chlorination I'm giving. Okay, assume that I'm adding a chlorine, all of you. So, you know what will happen here? You will add Fe anhydrous AlCl3, FeCl3, anything you add. So what will happen? These two chlorine bonds will break, right? It forms plus minus. This Cl minus will go to AlCl3. So what is the electrophile you generated here? Cl plus, right? Yes or no? Understood? No? One of the chlorine is taken up by AlCl3, right? So Cl plus will be attacking reagent, right? Electrophile. So one Cl here, one Cl here, another case. Ortho and para isomer, simple. Same story. That's all. This is your halogenation. It's bromine also you can do. Chlorine or bromine. Okay. Yes. For where is the double bond? Huh? Oh. Okay. Arnav, Tanishka, Tanvi, Vaibhavi, Shreya. Yes. That I missed. It's a part of electrophilic substitution reaction, not with the reaction of metals. Okay. Ananya, you got it now? Shaurya, you're clear? Pranav? Okay. So we had a discussion on that. So guys, quickly, can you tell me at least the IUPAC name of both? So 1 comma 2, yes, 1 comma 2 dichlorobenzene and the other one 4 dichlorobenzene. Yes, 1 comma 4 dichlorobenzene. Simple. It's very easy. No, if you want, you can say orthochloro chlorobenzene, right? You will take the whole chlorobenzene, one of it, and you can say orthochloro. Okay, here it's parachlorochlorobenzene. Okay, but it's not orthochloro terms when you're using it's a common name, not IUPAC name. So you need to stick with IUPAC name. Clear, no, everyone? IUPAC name is accepted. Okay, in the exam, generally they ask about IUPAC name. Okay, now all of you now give the headline. We will just go to the last part of this, haloarenes. That is preparation method. Okay, we are done with the chemical reactions. So give the headline preparation of haloarenes. Haloalkanes, so we have done it completely. So guys, now, so write down the headline preparation of haloarenes. Okay, preparation of haloarenes. So see look at the first method, guys. So in the first method, what are we doing? We are taking a toluene. Can you see we are taking a now in the toluene we will do chlorination. What we will do, guys? Chlorination. All of you write it down. And remember the chlorination we are carrying out. Okay, in the toluene, right? It has to be taken in the dark. Means no sunlight should be there. Otherwise, some other reaction will happen. So it's important that you mention dark. Okay, all of you write it down. And after you carry out this reaction, now understand here one important thing that this toluene has CS3 group as a side chain. Yes or no? Who is the side chain here? CS3. Remember, CS3 groups are electron donating groups. What they are? So when they donate electron in the ring, they are also ortho and para-directing, just like halogenes. They were donating electron inside the ring, right? So any group, any side chain who donates the electron in the ring towards the ring are ortho and para directing. So you people are smart. So what is your electrophile here? Cl plus. So write down the answer. It's very easy. Everyone write it down. So orthohalotoluene and parahalotoluene, right? Aditya, you got it, no? Yeah, perfect. Okay. And who will be breaking this bond, guys? Just dark is not enough. You put the element name Fe. Okay? Is it clear, no? Fe. If I put FeCl3 or AlCl3, it becomes then, it will become some other reaction. That is as, Friedel-Crafts reaction, right? And in place of Cl, we will take methyl chloride, right? Alkyl halide. Got it, no? So Fe will pull one the Cl, right? In the dark case. So the answer is, you will be getting this. Guys, please see this. CH3 and you will have Cl plus CH3 and Cl. I hope it is clear. Is everyone clear? Understood, everyone? So this is the first method. You can see we have got a haloarene, right? When a benzene ring is directly attached with a halogen group, it's haloarene, right? So this was the first reaction method of preparation. Now we will see another one. Write a note. And guys, remember one more thing. If they ask you, this is a para isomer, right? And if this is a ortho isomer. If they ask you between para and ortho, both the isomers, what is there, how is their melting points? So you have to write a note. Para isomer, para isomer has more melting point than ortho isomer, okay? The reason now, we are talking about melting point, guys, write it down. Reason you have to write, okay, the reason is para isomer is more symmetrical. Guys, para has more symmetrical structure, okay, and fits better in crystal lattice and fits better in lattice, right? You know the arrangement, right? So when the lattice in lattice crystal lattice is more stable, they will have more melting point. You need to put more height to break its lattice form, right? Because of symmetrical structure, they'll fit better. Yes, para is major as well as para has more melting point. Because it's more symmetrical, so it fits better in the lattice structure. Is it clear? No? You know, every solid form has a lattice, right? Correct. So they have a better arrangement. Online, is everyone clear about this? Please confirm it once. Sure, you got it, no? So write it down. Due to difference in melting point, they can easily be separated. Please take a note of this. Because there is a difference in the melting point, they can easily be separated. All right. Is everyone done? So guys, online, please tell me now. I'm going to tell you the last reaction of the day and the last preparation method also. Okay. Okay. Now what I'm going to tell you is very, very important. Look at this first. Guys, what is this? Can anyone identify? This is called aniline. What do we call? This is called aniline when the ring has an H2 group. So in aniline, we will add NaNO2 plus HCl. They react to give you HNO2. What they react to give? HNO2, which is freshly prepared nitrous acid. HNO3 is nitric. HNO2 is nitrous. Okay. So freshly prepared nitrous acid. Clear? Got it? Advitya, you clear, no? See, in some textbooks, this HNO2 is also written as HONO. Ananya, can I write HNO2 as HNO? Okay. Now, what will happen due to this? Due to this, you will have this structure N2 plus Cl minus. So, aniline changes into diazonium salt, benzene diazonium. Diazo means N2. N2 is called diazo. And it's a salt, positive, negative, right? So we call it as benzene diazonium salt. Benzene diazonium salt. So guys, tomorrow we are ending this chapter and we are going to do a lot of questions. Okay, and afterwards we are starting a new chapter, that is alcohol, phenol, and ethers. All right. Now, okay. Understood till here, everyone? The reaction. Diazonium salt is always formed, and this reaction has a name. Whenever you convert, guys, remember, whenever you convert aniline to diazonium salt using this, it's called diazotization reaction. Diazotization. Diazotization reaction. One student I remember, still I remember, has wrote in the exam demonetization reaction. Okay. So guys, it's diazo. Azo means, nitrogen, nitrogen bond. N2. Got it? Clear? Diazotization reaction. Now, why did we do this reaction? Okay. This same reaction you will study in amines chapter. I have to teach you here. Again, you will study in the same. Okay. So all the four chapters, what are those four chapters? Haloalkane haloarenes chapter, and then alcohol phenol ether, then aldehyde ketones and amines. All these four chapters are interconnected. You will see a lot of things what you're studying here, you will study there also. They all are interconnected. Okay. Now understand what I'm telling. NCRT has given these four chapters separately, but I as a tutor or you as a student should consider these four chapters as one chapter because they all are one. It's just you're studying in parts. Okay. Now, why did I told you this reaction? Because from diazotization, you will be studying in the next class two reactions. How many reactions? Two reactions from where we prepare haloarenes. What are those two reactions? It will be a Sandmeyer reaction, name reaction, Sandmeyer's reaction, and you will study Gattermann reaction. Okay, Sandmeyer and Gattermann. Don't write Gutterman. Okay, is it clear? It's Gattermann reaction. All right. So these two reactions we will be learning in the next class, and we will see how using this benzene diazonium salt we prepare halogens. All right. And some more reactions. After that, we will do a lot of questions. All right. All right, guys. So let's keep it till here, and I'll see you tomorrow at the same time. Bye, everyone. Yeah, tell me what doubt you have. Yeah, thank you, guys. Bye.